So next is defining the architecture of the neural network. So for this model, we will be using the sequential model. Why sequential? Because mostly for image classification tasks, this is the best model. It makes a linear stack of layers which is appropriate for image classification task. So we will define all our layers in between these down brackets. So this is how we will define our layers. So we'll have total 8 layers as discussed earlier. And our first layer, how do we define layers? We use the keyword layers dot. So this is how we define our layer. We have defined our first layer here, which is a convolutional layer, and this is the parameters of the convolutional layer. Let me explain how. What are these? 32 means the number of filters that we will be applying with this layer. So that means this layer will scan the image 32 times, and each time it will try to learn a feature, a prominent feature that can help us categorize the image or identify the patterns or edges or shapes of the image. Then what is 3 by 3? 3 by 3 is this window size that is going to be scanned within each feature map. Uh, with each feature map, it is going to take a window size of 3 by 3. It is going to scan it and it is going to learn a feature from it. Then this is the activation function, ReLU. Activation function is an important function that we use. Activation function is really important when we are working with layers because the activation function plays a number of roles, but the most important roles is that it helps the model to understand that what kind of input it has to take and what kind of input it has to ignore. So in case of ReLU, what it means is that it is going to ignore anything that is below 0. It will take anything that is above 0. So if there are negative values for pixels, those are going to be ignored, and that's the main purpose here. Then we have the input size, and input size determines the size of the image that we are going to feed into this layer. So the size is going to be 32 by 32. That means it is going to be of the width and height 32, and it has 3 color channels, that is RG and B. Then comes our second layer, and our second layer is a max pooling layer. And a max pooling layer, as discussed earlier, a pooling layer is something that is going to downsize the image size. So why do we use it? Because we want to reduce the complexity of the model. We want to eliminate all the values that does not serve any purpose. So here we will use a pool size. It needs a parameter for pool size, and here we are going to use a pool size of 2 by 2. And what does that mean? What does that mean is it is going to within each feature map, it will take a size of 2 by 2, and it is going to eliminate all the pixels within that size. It will eliminate all the pixels that are not determining something specific, something significant. So basically it will reduce the size by half. For example, let us take if the output of the size from layer 1 is 32 by 32, it is going to make it 16 by 16. Then comes our third layer. Our third layer is again going to be a convolutional layer, CONV 2D. And this time we are going to take a filter size of 64 because now we want the layer to focus on deeper details and try to understand features deeply so that the output uh, help us classify the image. So we will use 64 filters. That means we are going to create 64 feature maps out of this layer. Then we'll give it a window size of again 3 by 3 and 3 by 3, and our activation function, again we will use the ReLU activation function. And that's it for this one. So because we do not need to mention the input size, because these are layers and the output of one layer is automatically going to be fed into the next layer. Okay, so then a comma, then comes again our max pooling layer, and it will again serve the same purpose. Again we will take a size of 2 by 2 to downsample our image feature maps. Alright, then again we will take a convolutional layer, and this is going to be our final convolutional layer. So we will again take 64 filters. We want to capture every detail. Okay, and I forgot to mention the activation function, and again we have taken ReLU as the activation function. Then comes our flattened layer, and the purpose of the flattened layer is the output from the convolutional, the last convolutional layer is going to be a 3D output. So what is the flattened layer going to do is, because we want to generate a single output out of the entire input, so flattened layer is going to combine all of these inputs into a single dimension. So it will give us a value in 1D array, 1D array. It will us a 1D array, so that we can fed that into our dense layer, which is the most prominent layer of the architecture. Dense layer is a fully connected layer. By fully connected, we mean that in dense layer, all the neurons are connected to every other neuron. So what does that mean is, if we see in this, what does that mean is, if we see here in this image, so this is our dense layer. So this, in our dense layer, only for example, suppose there are two neurons. So the two neurons are, this neuron is connected to every other neuron in the next layer, and this neuron is connected to every other neuron in the next layer, because we want to create a single output for for as many nodes as we have taken into the dense layer. This is the input and this is the dense layer, and we want to generate an output for all the values of the input. We want to create as many outputs as we desire, so that we can make a decision, so that we are able to classify the image. So dense layer, after the dense layer there is going to be our last layer, which is again a dense layer, but this time it is going to have only 10 10 as parameter, because it is going to have 10 nodes, where each node denotes to one class out of our 10 classes that we have taken in the dataset. That means we have one node is going to specify cat, one is going to specify automobile, airplane, and so on. For each of the 10 nodes, we have 10 nodes. Uh, that what I mean is that the final layer will take the all the input take the all the input, and each node will process all the input together, and it will generate an output which is going to signify whether it belongs to that specific class or not. Then the second node is going to do the same. It is going to take every input, it is going to process it with the weights and the biases associated with that particular class, and it is going to generate a value that signifies whether it belongs to that class or not. So uh, similarly, we are going to generate 10 values at the output, and each value is going to signify the class value. So we will see it when we test our model that how this functions actually. So for now, this is the architecture of a model, and next we have to run it. Next comes compiling the model. So compiling the model means that we are going to put together all the things that we are going to need for the model. So how do we compile the model? So we take the model that we have defined earlier and we use the function compile, and the parameters are going to be the optimizer, the loss matrix, and the metrics that we want to evaluate our model. So the optimizer for this, the optimizer we are going to use is the Adam optimizer. So it is it what an optimizer do? It is going to, so we have weights in our model, and with the help of the weights we process the data, and optimizer is something that is going to optimize the weights when the model learns from the processing of the data and it generates the output, and sometimes it generates the wrong output, then it learns, and then the function of an optimizer come into place. The optimizer then revises the weight so that next time we produce the output, it is closer to the expected output. So this is optimizer. Then is the loss function. The loss function here we are going to use is from the keras. Okay, so the loss function that we have used here is a sparse categorical cross entropy loss. And what does a loss function do? Loss function indicates how much our output differs from the expected output. So it helps the model understand that how far is the output from the actual output, and that on the basis of it, the Adam optimizer optimizes the weights, increases them or decreases them, so that the next time it produces the output, it is much closer. And it will also used to evaluate our model, that how well our model is performing. Then comes metrics. Metrics essentially is just to understand the evaluate the model, that how well it performs. So here we are going to use accuracy, but there are different kinds of metrics that we can use. Because we are working with image classification categories, we can use the categorical accuracy. So accuracy is the overall accuracy, and if we use categorical accuracy, it will calculate the accuracy over classes, like whether it was able to, for example, there is a class of a cat, and we will judge whether it was able to um, uh, classify all the images that belongs to the class of cat rightly or wrongly. So there are different kinds of metrics, but for this model we will use accuracy because it's the simplest. So now let's run this. And yes, and next, the next part is training the model. So how do we train a model? We have defined our model, we have compiled it, we have given it all the information that it need to run. Now we'll train it. That means we're just going to feed into our training data to the model, and the validation data to validate the model, that whether it has started functioning well or not, and define some other parameters that we will discuss. So we are going to train our model, and we are going to put it into a history variable, because then the all the because when our model gets trained, it is going to generate some variables, some parameters that we can use to visualize our model, how is our model functioning. So we'll just use history as a variable, and then we write the name of the model, and then we use fit function to supply our training data to it. So we passed xtrain and y underscore train. So we have passed our training data. image and the associated labels, and then we are going to define our epochs. That means it tells the model that how many times it has to iterate over the training data to learn from the losses. So 10 means it is going to iterate 10 times over the training data, and each time it is going to calculate the loss and then try to perform better the next time. And this is what we will try to visualize in our plot, that has it performed better after each epoch or not. So yes, we have defined 10 epochs, and then there is also something that is called validation. So what does validation means is that after we have trained our data, trained our model on the data, we need to validate it against some new values that it hasn't been trained on. So we give it a data that it hasn't seen before, and it tries to predict all the labels for that data, and then it tells us whether it was able to predict them correctly or not correctly, and that signifies that whether the model is performing well or it is not. So here validation data will be using our testing data as the validating data. However, you can also divide your training data into two portions, again the validation and training, and then use it. But for now, let's just use the testing data as our validation data. So this is it. We have defined the parameters to train our model, and this step is going to take some time.